Okay, so actually, I read the paper you sent last time. I tried to read, but I probably understood some of it, but definitely you need to do some explaining to me. Okay,
Okay,
I think the topics today was ether. And
right.
also, automatically, the moment people hear the word ether, they thought it's an obsolete concept. Only the pseudoscientific people talks about it, or sometimes even they say we already disproven ether doesn't exist. So what's the point? And we have a model that explains the stuff without any need for ether. So that's the consensus from the scientific point of view. But
Yeah.
my question is, why the concept of ether persists? And why people,
Why does the concept of ether persist? I
even
think
though
it's
even though main scientific consensus tries to discredit it and they already said it's disproven, but the people are still studying it. So why the
yeah.
concept
I
still?
don't I don't think it's wise to
Mhm.
okay, here's what I think happened back in the day. And I think we talked about this a bit last time. So they had a model for the ether.
Mhm.
Okay, they had their own idea, and actually Maxwell, I think, had they all had an ether, the idea of what the ether was, and they thought that that say a planet is going through a static ether.
Mhm.
Okay, so the ether is static, and we're going through it. And
Mhm.
so if that was true, they made some predictions and said, well, this experiment should show, some difference going in different directions. So when we shoot a light beam straight, it should come back at a different time than if we shoot it out to the, laterally
Mhm.
or medium, whatever, like in different direction, 90 degrees orthogonal to each other. And so what they found was the light came back at exactly the same time. And therefore, they said, therefore, there is no ether. Okay. So they didn't actually disprove, you can't really disprove something. You can only really prove something exists, right? And
Mhm.
so they had a model of the ether that was maybe wrong. I think it was the wrong. I don't think it's a static ether. I think it's a dynamic ether.
Mhm.
If it was a static ether, then they disproved basically a static ether.
Okay.
But just because you disprove the wrong model of the ether doesn't mean the ether doesn't exist.
So
You know what
based
I'm
on
saying? So basically, I'm saying there can be an ether. Not that there is or isn't, because I don't think anyone can say that,
Mhm.
right?
Mhm.
So just because you don't prove something doesn't mean you
I agree.
disprove.
I agree.
Okay? Yeah, good.
So based on Maxwell's equation of electromagnetism,
Mhm.
he needed an ether to explain the waves, right? And that's
Yeah.
why later sciences are trying to prove if there is a ether, let's characterize it, let's measure it, etc., etc. But their
Mhm.
original theory required a ether
Yeah.
for the medium, right? Because
Yeah.
otherwise,
He
without
was.
medium, without the wave cannot move. That was the
Yeah.
basic idea. Okay,
Yeah, like
okay.
like everything else, like all other mediums, like water, air,
Hmm.
your body, which ultrasound needs a medium. Like all anything that propagates a wave
Hmm.
seems to need a medium.
Hmm.
Now, the problem with the ether is that light travels through what we call empty space,
Yeah.
right? Okay, so whatever ether is, it can't be like atoms.
Hmm.
It can't be what we perceive as ponderable matter. I call it ponderable matter
Hmm.
would be like an atom and an electron, like things that we can actually physically detect and measure. A lot of people actually don't think the electron exists actually, but I'm not really going, I don't really go there. Like the electron is a phenomenon that exists, whether
Yeah,
it's a
yeah,
particle
yeah.
or a
Not
wave or something
necessarily
in
a
between.
particle, exactly. But
Yeah. And
obviously, it
so
exists as a wave because otherwise, how can you see, right?
yeah. So the ether can't be hydrogen atoms, and it can't be electrons, just
Hmm.
electrons, or it can't be that, because because a light propagates in empty space where there's supposedly no matter, like between galaxies. It's pretty much empty space, supposedly. I think there's a lot of like other kind of physics going on there, like plasma physics, and there are charged particles going through the universe. So it's not completely empty, but the fact is that light travels from a galaxy and gets to us, and it's a clear signal. Like it's it's not a it's a fuzzy picture, but the resolution is quite good considering how far away those things are. When we take pictures of galaxies, you see a lot of detail, and so the light can't be like, whatever the medium is, it has to be like, something that is not matter, because matter, like electrons, deflect light waves and that sort of thing. So the idea I came up with, and it's not really my idea, but an idea that I gathered from studying like a whole bunch of people, is that the medium for the propagation of light is electron-positron pairs. Now, can I share my screen now? Because I think I had made a few slides that might.
Sure.
So there is.
Yes.
So, okay.
Now you can see exactly.
Okay, so I just made a slide of the title of of my paper, and I don't know if you want me to read it or
Actually, because it's a public paper, anybody can see. So many people already read it. I also read it, but I can ask you a very specific question. But why not you just present the finding?
So let's look at this picture here. So this is a figure from the paper. And so the idea I had that came from a guy named Ernest Sternglass. I don't know if you ever heard of Ernest Sternglass, but he was quite young, like when he met Albert Einstein. Okay, so he met Albert Einstein when he was just finished graduating as an undergrad, and he went to visit Albert Einstein, and so he had a theory. And he's got a book called Before the Big Bang. Before the Big Bang. And so his idea, which I am leveraging pretty much, is that the universe began before the Big Bang as a relativistic electron-positron pair. Okay, that's what he called it. So you can imagine, so you've heard of electron-positron pairs, right? When an electron and a positron come together, they annihilate. You've heard of that? Okay, so when you have an electron and a positron, you bring them together, they supposedly annihilate. They destroy each other, and they release
matter, antimatter.
Matter and antimatter. When they come together, they release a whole bunch of energy, and they supposedly disappear. So, but what Ernest Sternglass said is before the Big Bang, the universe was a relativistic electron-positron pair. So they were together as one thing, right? And then they in his model, there was like a cell division kind of a process where it divided, and then there were two, and then it divided, and then there were four, and then it divided. Then so after about 270 cell divisions, supposedly. There was a phase transition that created the rest of the universe, that the matter came after that. Okay, so the idea is that the universe is filled with these electron-positron pairs, that when they annihilate, they don't completely disappear, that they fall back into what I call the medium for the propagation of light, the ether, right? So the ether is not made of atoms, it's not made of electrons, it's made of electron-positron pairs that are paired together kind of like a magnet, kind of like a dipole. So they would come together as a kind of a dipole. And that fills space. So space exists because these things fill space. And that becomes the medium for the propagation of light. And so what I did in this paper was I showed the math to prove that if the universe was filled with electron-positron pairs, that the speed of propagation of such a medium would be the speed of light. Right? So I used an analogy with something with sodium chloride, with salt crystals. And so I used an analogy of a medium that we know, that we understand, that we can look at and measure. And so I use that analogy in the paper to prove that, you know, if the space was filled with a medium of electron-positron pairs, that the speed of propagation of that medium would be the speed of light. And so,
So
so that's,
how can you can you explain in your sodium chloride solution crystallization and dissolution of that crystal relates to the Michelson Morley or speed of light calculation? Can you explain that?
Okay. Yeah. So now you can probably see my paper.
Yes.
Okay. So I'm just going to scroll through. So I'm just going to read a couple of claims from my paper because that kind of sets the foundation for everything else. So the claim is that all waves are caused by perturbations of a medium, waving. Okay, so in order for a wave to form, something must be waving. So it can't be nothing, can't be empty space, has to be something. So all wave propagation requires a medium, and I say there are no exceptions. So we know that, you know, water, there's a speed of sound in water, there's a speed of sound in air, there's a speed of sound in sodium chloride, in salt. And so the speed of sound in sodium, so there's an equation that we use for calculating the speed of sound in a material. Okay, so this is the equation right here. So the velocity of, and we use this in medical imaging to make phantoms, to make realistic phantoms, to model human tissue. So we put together a material that's made of agar, which is a kind of jello, and we put other stuff in it, and we test it to make sure that we want to test things in an approximate speed of sound of tissue, of human tissue, so that our measurements, you know, when we experiment with our devices, that we get good results. And so you can actually make materials for the sound wave to propagate at certain speeds. Okay. So sodium chloride is, you know, a material when it's in crystalline form, right? So when it's in a crystalline form and it's pretty much clear, pretty much transparent, okay, it's got so this is the equation you use to calculate the speed of sound in any material. So it's so here you have the square root of what would be called the stiffness constant, which is that would be the stiffness of the material, that would be the elasticity of the material, right? A material that's stiff but elastic will you know, spring faster. So if it has a high spring constant, then the speed's going to be fast. But if it has a high density, in other words, if the atoms are massive, right? If the material that the medium is made of has more inertia, then that's going to slow down the speed of sound. So these two things sort of work together to conspire to create the speed of sound of any material. Yeah, so the example is going to be the sodium chloride because it's it's a simple example because it's made of sodium, like two ions, right? So there's the sodium ion and the chlorine ion, and when they come together and they bind, okay, then this constant defines how they bind, the strength of their binding. So this is really the binding energy of the material. And so, and then when you take, say, the mass of one sodium atom and the mass of one chlorine atom and add them together, then that would be this parameter down here. And then you would divide it and you would get the speed of sound. And sure enough, when you do that, when you take the binding energy of sodium and chloride in a sodium chloride crystal and divide that by the mass of the sodium and chlorine atoms, you get the correct speed of sound of the medium. Okay, so it's a crystal, you know, you got sodium, you got chloride, and that's it. That's all you need to calculate the speed of sound of the sodium crystal. Now, what happens with sodium, with the salt crystal, is if you bombard it with a certain amount of energy, like I think it's UV energy, 8 electron volts or something like that, then what happens is the sodium and the chloride, they actually come out of the crystal, and they're allowed to move freely within the medium.
Mhm.
And then when you take the light away, it falls back into the crystal. So that's the analogy. So then I just take the sodium and the chloride and replace that with the electron and the positron. And when I plug those into this equation, I get the speed of light.
Okay.
Right. So so the medium the medium for the propagation of light, if it was made of electron positron pairs, either dynamic moving, or I don't think they're in a crystal necessarily like sodium chloride. So because I don't think the ether is static, but it doesn't really matter what the medium, because water is fluid and it's a medium, and air is fluid and it's a medium. So it's more like air and less like sodium chloride, but every medium uses this equation to calculate the speed of propagation. Okay. So when I pretend that the ether is made of electron positron pairs, I get the right answer for the speed of light. Right? So basically I'm saying there can be an ether. Not that there is an ether, but there can be an ether. And when there is, when you have this as the ether, it actually simplifies a lot of things. It explains a lot of things that are very mysterious, like what is charge and what is magnetism, and what is a field, so these are things that are very difficult. Without a medium, they're very difficult you have to invent crazy quantum mechanics to understand how these, or to try to explain how these things are working.
So regarding the old theory of ether versus modern theory of quantum field versus Higgs field, they are very similar concept, because they are saying that the quantum field allows light to propagate.
Yeah. And so so the language is getting closer.
Exactly.
They denied the ether, but then they keep like sneaking it in. Like Albert Einstein, what did he call it? The fabric of space-time. Well, that's the ether.
Exactly.
Right? So they deny the ether, but then they kind of sneak it in with they change the wording and give it a different name. Exactly. But it's still the ether. So you're right. Like, so there can be an ether. There doesn't have, if you don't want an ether, then there doesn't have to be an ether. But if you do have an ether, I find, at least with the ether that I'm trying to, see if I'm right or not, solves a lot of problems. So if it makes things simpler, if having an ether makes it simpler, then we should have an ether.
Exactly.
That's Occam's razor, right?
Exactly.
Right. So that's my I like things simple. I want things to be simple, and I want to be able to apply the same laws. So here's the equation for the speed of light that they use. They make it look a little, so we know that space has properties. We know the media, whatever light is traveling in, has properties. So how can nothing have properties? It's got the property of permeability and permittivity. That's what these symbols, stand for. And so, I can rearrange this equation to look exactly like the equation I used earlier for the speed of sound in a material. And then you realize, oh, there has to be a medium. There is a medium, and then you have to ask the question: what is it made of? Well, it's not made of atoms. It's not made of just electrons. So what happens is, I believe the electron positron, the electron positron pairs are bound together, and so when they annihilate, they fall back into the medium. It's kind of like if you throw water, dump your water bottle into the river, it's just going to become part of the river, right?
Yeah.
And so, that's, so here's what happens when the electron positron pairs annihilate, they emit 2 gamma rays, right? The two gamma rays propagate through the medium. So they lose energy when they bind back into the medium. And the same thing happens with the sodium chloride. When so before I said the UV light makes them come out of the lattice, But
Mm-hmm.
then when they fall back in, when they rebind into the lattice, they emit the same energy that was used to pull them out. And that's the same with everything. Like that's even why light exists, is because materials are absorbing the energy, and then when they bind, so that when two things bind together, they actually release energy. And that's the point I think a lot of people miss. I don't think people realize. They think, oh, but when to bind something together, you need to add energy. No, when things bind together, they actually lose energy. They become in, they have a lower energy state, and then you have to put the energy back in to take them apart.
Okay.
And so when the electron positron pairs fall, when they come close together, they annihilate, and then they bind. When they bind, they lose almost all of their mass energy,
Okay.
except for a tiny, 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 tiny little bit, really, really small. So they still have mass, but the mass is so small that it might as well not exist.
Okay.
And
So,
that's why it's hard to detect, because the medium is very inertialess. It's uninertia. You can call it uninertia because it has very little inertia. Just like air. Like air is very inertialess compared to, say, water or something heavier, right?
so based on your paper, you're saying for the sound, the equation that we conventionally use requires two related parameters. One is stiffness or springiness versus density. So
Yeah.
for the speed of light, you still need very two similar concepts. And because the similar concept gives you accurate result, indirectly it suggests there should be a medium for the light too.
Right.
So that's the
Yeah.
summary for the general public without any equation, right? So far?
Yeah. That's a good way of putting it. Yeah. Yeah.
Okay.
And so with this equation here, so there's the stiffness constant, which is on top. That would be inverse permeability here, but if something's really stiff, right? So for the speed of light to be super fast, like the way it is, it has to be extremely elastic. The stiffness, extremely elastic, but it also has to be almost inertialess. Like, so the density has to be really low, right? So that's how, that's again why it's very difficult to detect, because the density is very low, but it's got a super high elastic constant. And so that's why the speed of light is so fast compared to any other, material medium.
So in general, because I'm not expert in this field, so I'm just asking a question. So in general, the more solid a structure is, the speed propagation through that particular wave, for example, sound is higher, right? For example,
Correct.
air versus
Yeah.
water speed is higher, right? And versus metal.
Air is in the 300 and something. Water is like 1496, I think.
Wow.
Sodium chloride is around 3600.
Okay.
And these are the only ones I memorized. Diamond is around 12,000.
Okay.
So diamond, of course, is much harder, much stiffer than sodium chloride. I can break a sodium chloride salt crystal, with a hammer, and so the diamond, which is much, stiffer, is like 12,000 meters per second, whereas the sodium chloride is like 3,600.
So by the same extension, because the speed of light through the ether is so fast, so their stiffness has to be very high.
Yeah, right? The stiffness has to be very high, but the density, the stiffness has to be really high, and or the density, the whatever it's made up of has to be like really light. The whatever. So the electrons and positrons, they're fairly light compared to a heavier atom. And so so the density would be the addition of the mass of the electron and the mass of the positron would make up the bottom here. So between the two, so you have a high stiffness and a low density, it makes this value here super, super big, right? So if this is smaller, if this is bigger and this is smaller, then this is going to be big. So it's a combination of two. super, super stiff. But some people confuse stiffness with, oh, ether can't be stiff like steel. Like it's not steel. It's not like that kind of a solid, right? It could actually be a fluid and be super elastic, right? So it took me a long time to wrap my head around this, but you know, the more I thought about it, the more I realized, you know,
Yeah, I think in this point I can compare an analogy. For example, a plastic wrapping paper that you put on the food is it's very thin and very light, but when you tighten it,
it's super elastic.
That can transmit a vibration very good.
Yes. Oh yeah, that's a really good example actually. Yeah. Yep.
So ether must be very light but very stiff. So in theory,
yeah. So I think you get the idea. I mean, this is, you know, ridiculously, but still, I mean, yeah. So my calculations with and it doesn't even have to be like any particle antiparticle pair, you know, will fall back into the ether and become part of the ether. But we don't really see too much of that. We mostly see electrons, so electron-positron pairs in nature, you know, because they exist. We know they exist. A lot of people say, oh, electrons don't exist, but, you know, there's a such thing as a positron, you know, positron emitter. We can emit positrons and we can emit electrons, and, you know, our old CRT screens relied on the idea that, you know, it's an electron beam. So, you know, I'm not ready to deny the electron yet, but there are a lot of people out there that really want to deny the electron.
Okay.
You know. Okay. But obviously the phenomenon we call electron does exist. Whether it's a ponderable particle that, you know, obviously it's not a particle you can hold in your hand, like sodium chloride, right? So it's different. But yeah.
Even for photon, because we're talking about speed of light, I have just a general question. So if you say something is massless, no weight, but you're claiming they can still have effect like a momentum, like a photoelectric effect?
I have a good answer for that, I think.
Good. Okay.
What's the mass of a water wave?
It's nothing actually. It's just a function, right? Rather than actual thing.
Yeah. So same with light. What happens? So I spend it because, you know, of the cabin, we spend a lot of time on the beach, and I spend a lot of time watching waves come in or standing in the waves, right? Because when you go into the water and you stand in the wave doesn't push you back. The wave pushes you up and down. It kind of pushes you in a circle. Right. So if you had a wave, you were watching the waves go in, and you put something in the water, a little piece of styrofoam or something, it's going to float. It's not going to go that way. It's going to go in circles. Okay. It's not going to, right? Yeah. So the water isn't moving. The water isn't moving. The water is moving up and down, but the wave is propagating towards the shore.
Okay.
Right. So then the wave is massless. The wave is just the water going up and down. The water has inertia, the water has mass, but when the wave is propagating, the water is just going up and down. The wave, you know, so that's obvious when you think of it that way. But so this is the wave particle duality, I guess, that we're getting into. So what happens when the water hits the shore?
Okay.
Right? It crashes, right? So if a wave is coming in, it's a wave until it hits the shore, then it breaks, then it crashes, then water is moving. When water crashes, right, on the shore, then the actual water is moving, then you have momentum, then you have the actual water moving, and that's going to push you over, that's going to push me over. If I'm standing where the water is breaking, it's going to knock me right down.
But that particular moving part also being contributed by the shore, how the shore is structured, right? It's shallow.
That's, exactly.
The deep water in the middle of it.
And that's exactly it. And so imagine your eye being the shore of the medium for the propagation of light. So when the wave crashes on the shore of your eye, then your eye perceives it as a particle. It's not a particle, in my opinion, until it hits the shore of the detector. So it might not be an eye, it might be a CCD camera, it might be a whatever, but X-ray detector, whatever. But in my opinion, it is not a particle until it hits the shore. You know, but between where it was emitted or where it was, you know, created, and then when it reached your eye, in between, it was just a wave, just like a wave on the water, right, which is massless. So that's where the massless, yeah. So a wave, all waves are massless, I think, I believe.
Okay. Yeah, by definition, if you don't talk about particle, just talk about the wave, by definition, wave should not have any mass, because I think the way I understood, I think you also mentioned before, wave is a function rather than actual stuff, right?
Yeah, it's a, I mean, it can be described as a function, mathematically as a function, right? But a wave is just, I usually call it a perturbation.
Okay.
So, you know, let's say you're sitting in a pool of water and you wave your hand back and forth, right? You're perturbing the medium, the water. And when you do that, it makes the water, you know, waves. You're waving the water. Unless something is waving the water, there's not going to be a wave, right? If there's a pool and nobody's touching the pool and, you know, it's not windy out or anything, then that water is not going to move. So in order to create the wave, you need to perturb the medium, and that's what happens when you create light. What's happening is whatever it is, let's say it's your lamp, right? What your lamp is doing is it's wiggling the medium. It's wiggling the medium. It's, you know, vibrating it, create at certain frequencies that, you know, you can see, and because it's emitting, you know, like it. So people always say, oh, light is emitted. They use the word emitted, and that gives you the idea that it is spitting out something. That it is that, you know, something is coming out of the lamp and propagating, you know, or like a ball being thrown down the road kind of thing. So when you use the word emit, you kind of get the idea that something is being spitting out, right?
Yeah, that's
that kind of thing.
Idea.
And so I don't know if that's the right way of looking at it. I'd rather, you know, it makes more sense to me that whatever, you know, is creating the light is vibrating the medium, just like I would if it was in water. And that is, you know, of course, then the wave is what propagates down, you know, down the line. Right? It spreads out. So it gets weaker, you know, as it spreads out.
Yeah. When I read, actually, I was interested to see how actually light being produced. I think the official story that I read in the papers, they're suggesting when an electron jumps from one shell to another, it emits photon. Suppose that photon is actually the wave rather than the particle. So now electrons are moving, creating a perturbation in the medium. For example, we are considering ether to exist, for example. Then when the electron moves, it creates the perturbation in the ether that we call photon, something like that.
That's the idea.
And that's that. So we are,
and that makes sense.
Because I'm an outsider, so I'm just trying to
Oh no, you're asking good.
With you,
I'm not a total insider either.
I'm way outsider. So sometimes I try to reconfirm my idea with you, so that.
Well, you know, you have a good knowledge base, obviously, and you know what mainstream is saying, which is a good start. You know, I'm not really against mainstream, but I do go, you know, I am going in a different direction than what they're doing. But you have to know what they're doing before you can change it.
My goal is just to know whether it's coming from mainstream or alternative.
Well, I had to say, I'm the same. Like, I think I told you last time, I studied for years and years and years, and then I got fed up and said, I'm going to do it myself because I don't get it. It was too hard. I don't want it to be hard. I want it to be easy. And then I want to, if I, you know, then I want to teach it to other people.
Okay, so let's move on to the paper's next topics. I think after the sodium chloride, you discuss sound as a model for Michelson Morley's experiment, right? Something like that?
Yeah. Okay. Yeah. So actually, it's kind of interesting that you mentioned that. I totally forgot. I read a paper when I was doing this research. I read a paper, and a group had done an experiment, sort of a Michelson Morley like experiment in air. So instead of it being light, they were using the speed of sound in air. Okay, and so what they did was, so in the Michelson Morley experiment, they assumed they'd get a different reading in different directions because the Earth is moving through space. And so they figured they would see it, measure a different speed of light in the direction of motion compared to the not direction of motion. And so what this group did is they did an experiment using ultrasound transducers in air, and they were in a vehicle and they were moving, right? They were moving through space. The speed of sound is quite slow, so it was a reasonable sort of experiment to do, and they got a null result.
Wow! So
they got a null result. So in other words, they couldn't detect the difference in the speed of sound in the direction they were going compared to the other direction.
Yeah.
And so and they did some calculations to see if they, if it was statistics, or if they had enough digits of precision really to measure this, and they thought they did. And so, which is kind of ironic, because Michelson Morley said, oh, we got a null result, therefore ether doesn't exist. And these guys got a null result, so they'd have to conclude that air doesn't exist.
Yeah, that
right.
Yeah,
So
I have a comment here. So actually I also read that small paper in 1979. Probably that paper was published. I don't know any recent paper, but I read a paper in 1979. I can share you with that paper. But they're saying that they control the air flow, so they know the air is moving for sure when they did along the direction of the air versus in the opposite direction.
Oh yeah, okay. Yeah.
So they know the air is moving for sure, but still they're saying the speed appears to be same.
So whether the air is moving or not moving, or whatever the air is doing, and that makes sense, because the speed of propagation in a medium only depends on the elastic properties of the medium and the density of the medium. So if the air, it doesn't matter if the air is moving or not moving or what the heck is going on. It's right. And so that's why they got a null result. They were misunderstanding the problem, I think.
Exactly. But commonsensical idea is, for example, I throw a ball, and if I throw a ball from the ground versus if I throw a ball from a train, so the ball I'm throwing from the train definitely will be speedier, right?
A wave is not a thing. So that's where it gets confusing, like we talked about in the water. What's the mass of a wave? Well, it's got no mass. So you can't use the ball analogy with a wave. For the same reason, you can't use the ball analogy with a wave. The speed of propagation, now what might happen is, in one direction, you're going to maybe see a Doppler shift, but the speed of propagation of the wave I don't care what direction you're moving, the speed of propagation of the wave has nothing to do with your motion, right? It's going to be the speed of sound of whatever that medium is.
So for the sound, if the sound propagation is independent of the velocity of the air, it has nothing to do with the speed of the air. The speed of the sound has nothing to do with the speed of the air, right? But just because they could not find the difference by this experiment it's not designed to prove the air exists. Exactly. So that actually gives a very good idea. The sound experiment gives a very good idea. Actually, Michelson Morley experiment is not designed to detect the ether, because their assumption was it should increase the speed of light, but that assumption is false, even for the air.
Right. Yeah. So it was just wrong thinking. It was they made the wrong assumption, I guess you could say.
Okay.
Yeah.
That's really interesting. So in summary, so far you have mentioned, let me assimilate whatever you said. Number one, the medium, there has to be a medium for a thing to propagate. So
for a wave.
For the wave, yeah.
Right. right? Yeah, because things are things and waves are, yeah.
Yeah, because light, if everybody considers, has a wave-like property. In order it to propagate, it needs a medium. Okay, now what kind of medium is this? You characterize the elasticity, stiffness versus density, and based on your model, actually the similar quality applies for the light propagation. And by extension, you are saying there has to be an ether, although Michelson Morley failed to detect, but it doesn't disprove its existence, right?
Yeah, right. So just because you don't detect the ether doesn't mean it doesn't exist. It just means you.
Yeah, that makes
you know.
perfect sense to me.
Yeah. Yep.
Okay.
Yep. So my hypothesis is that there can be an ether, not that there is an ether. Like, and I think that's the other thing is they are in complete denial. They're denying the ether. So just because you don't find the ether doesn't mean you've denied it. Doesn't mean you've proven that it doesn't exist.
Now,
right?
in this regard, I have a question actually. What's your gut feelings that why they're really selectively like eliminates the need for ether, because still they're talking about quantum field. That's a very similar term for ether, but why they hate the
I know. I really don't know. Like, I've had to deal with this for many, many years, and I get the same. This is how I've come to be able to defend this a little bit, because I get asked the same questions all the time. Oh, but Michelson Morley, wait a minute. No, he didn't. So I've had this argument quite a bit, and people are very insistent on this, and it's almost like you can't join the club unless you deny the ether. Right? Like, there's no way I'd be able to get my PhD on this if I'm denying the ether.
But my question was, if somebody hates something, they must have some reason, right? So it's not a random just hate that we hate ether. We don't need ether.
Yeah, that's a good question. There's a lot of conspiracy theories out there about, they just don't want us to know the truth, and they want it to be, they actually know there's an ether, but they want.
Does it make a big
keep
deal?
All the information for themselves. It makes it much more difficult.
Yeah. So for example, for the sound you need air to travel, so it's not a conspiracy theory. So for the light, there is a medium. If they disclose that should not be a conspiracy, because
I know why not?
I understand why the conspiracy theory is going in that direction. Mm-hmm. There must be some other reason that we don't know, but that's a simple explanation, right?
Yeah, I think it's just they don't want to give it up. I don't know why, because even Einstein, in his later days, like, maybe even the year or a few years before he passed away, there's a video clip you can find. You've probably even seen it on YouTube, where he says, relativity requires an ether, basically what he's saying. He said, I can't imagine relativity working without the ether. So he never gave up on the ether, even though everyone attributes him to coming up with an etherless theory, even though he had to invent the fabric of space-time in order to squeeze the ether back in there, but he couldn't call it the ether. So the word ether has become a bad word. I don't know why, because I want to use the word ether because it's a beautiful word. If you look up the roots of the word, this is exactly what we should call it. So, I get really mad when people say, oh, you can't call it the ether then. Well, okay, let me get this right. You denied the ether. You said it doesn't exist. So I can never, ever, ever use that word. Like, they hijacked the word ether.
Yeah.
And now I can't use that word because it's a bad word now. So that's really annoying, because it is the perfect word. It is the perfect word.
I think for those people who don't know, can you explain the term, the ether? I think you said there's a good meaning of ether, right?
It's kind of, I don't have the information off the top of my head, but I think if you look at the roots of the word, it kind of means air. But to me, it's how it sounds. It's like, it's the earth air, right? Ether, earth air. Like, it's, the universe wouldn't exist without it. And so that's, it's life would not exist without it. And so it is the air. Okay, to me, it's like the air of matter. Matter requires ether. Matter requires it to exist and persist.
I
And
think
so matter cannot exist in a vacuum. So here, okay, I'm going to show you this picture, and here's why I think so. Can you see this picture here?
Yes.
Yeah, I lifted this picture from a really interesting article by a guy named Don Hodson. So he's another person I studied, and he talks about electron-positron pairs as well in his theory. And so here's a depiction. So I want you to imagine that each of these little, so you can think of these are charges. This is a diagram you would see, you know, this would positive, negative, negative, negative. This is what the this is what the field, the electric field looks like, a normal drawing of the electric field. But why is there an electric field? Why? Where does it come from? What is it? Okay, so Don Hodson drew this drawing where each of these little things here is an electron-positron pair. And in the presence of, so let's say an electron and a proton are near each other. It is a positive charge and negative charge. Well, all of the little dipoles that make up the ether are going to line up like this. They're going to line up, right? Like this. And this is exactly what we see when, you know, like in a magnet, let's pretend this is a magnet now, and you threw iron filings down, you're going to see them line up in this pattern. So the ether to me is very, 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 very tiny magnets, very, very, very tiny iron filings, if you want to, but like they're dipoles, because the electron is negative, positron is positive. When they come together, let me just see. Can you see this?
Yes.
Right. It's a pot. I switched to a different view.
I can see the red dot.
Oh, good. So, so the red dot is a positive charge. This is a simulation. This is on my website, but it's actually this company here made it. I just put it on my website for convenience. But so you can see these lines, these arrows would be vectors. Okay, and when I move this around, you see the arrows move. And then when I move a negative charge in here, then you see what happens, right? So as you move the charge around, these arrows move. And so imagine that these arrows are electron-positron pairs instead of arrows, right? So when I move it around, these are going to point to, right? Like that, or point away from. But look what happens when I bring these two together. When I put them right on top of each other, the field disappears. But guess what? The charges are still there. The charges,
they're canceling each other, right?
The charges are still there. This would be like annihilation, right? Electron-positron pair annihilation. When they come close together, their field disappears, right? Unless something else comes close to it, and then then the field comes back. So that's kind of my analogy for the electron-positron pair. So if you pull the electron-positron pair apart, then they become more like a dipole. And let's go back to this drawing here. So the electron-positron pairs in the medium would line up just like we see in the field diagram. So instead of the field being just some imaginary thing that we don't know what it is, it could be electron-positron pairs. Like the field might in fact actually look like this, right? So without a medium, then how does this field appear? If space is empty between a positive and a negative charge, then how do you get this field? So this gives a physicality possibly to these field patterns that we know exist. We know they exist.
Can you go back to your animation, the animation screen?
Yeah. All right. There we go. Yep.
Yeah. So in this screen, if there is no charge, it's all pitch black, right?
Yep.
Okay. Now in this pitch black, so electron position, they are superimposed with each other and they are disorganized, so it's not detectable. Something like that.
Right. Exactly.
Now you put a positive charge because the positive charge can affect the electron part of electron positive pair, electron position pair. So they become little bit separated.
Yeah.
For example, electron gets attracted towards the positive charge, so it has to be separated temporarily from the positron, so it becomes manifested.
It becomes manifest, exactly.
Yeah. So that still the electron positron pair was present in the black pitch dark medium.
You could pretend that they are, yeah. So like in this situation, you can imagine that they're in there, and but as soon as a positive charge comes into the field, they react to it, and then they line up in a certain way.
Perfect. So this model actually works very good. Whatever you're proposing is self-contained without any contradiction.
Exactly. And it's easy to explain, and I haven't even done any math yet, except for the equation for the speed of sound.
But I think you should go for it, because if you put a very nice math and equation, people will seriously consider it. Just by the visual, many people, probably physicists, they like math. So probably they need some good.
I know. That's why, there's a bit of math in here. I mean, there's the few equation. This is pretty simple though, but so it's not too much math. So it doesn't scare too many people away. I don't,
Yeah, I think I understood reasonable amount because it doesn't involve calculus. My weakness,
exactly.
I forgot most of calculus, but regular math, I think I can still understand.
Yeah. I think it's fairly logical too, and with the pictures and the animation. That's why I like making videos. I think it's more understandable. Like a paper is great, and it's good for me to practice writing papers like this. But the videos, I get a lot more. I think people understand them better. I can put, animations and, describe things in real time. So
I think we are near the end of an hour. So in the last part, I will ask you just a random question.
Yep.
The question is, can you mention a couple of relatively contemporary scientists and also old...
mention what?
Like relatively contemporary scientists and some famous scientists in the history, they really believed in ether. For example, you mentioned, even Einstein mentioned that he really needs ether for relativity to work in the initial phase, right?
Yeah,
so
and I think
Tesla also believed in ether, right? So those people who are talking about ether, they're not just isolated people. They have support from famous scientists. That's my point. Even Einstein, Tesla, then Maxwell, I think many other like proponent of early quantum theory, they also believe because it's a requirement for their theory to work.
Yeah.
So just because we're talking out of the mainstream doesn't mean we don't have company. We have lots of famous people along with us, right?
Yeah. Einstein is my spiritual guide.
He's a smart guy.
A lot of independent researchers, they like to deny Einstein. They like to say Einstein's wrong, and I'm not like that. I think everyone can be right to some extent. Like I'm a very glass, mostly full kind of person. I believe that everyone has a piece of the puzzle, that everyone is partly right, and that all I have to do is gather all the puzzle pieces and put it all together. And so I feel like I've been collecting puzzle pieces for the last 30 years. And
as you just mentioned regarding your math skills, not so great, but I have a question regarding that. So when you work with your computer model, do you do math first, or you think about the process first, then do the math? Like for regarding any project, you first do math, or you first think how it should work, then formulate your idea in mathematical equation?
The math usually comes after. Yeah,
so I mean, the math is not the ultimate weapon, because
it's kind of hard to say, because sometimes I just take, like back in the day when I first got like my very first computer, I just plugged in math equations and just to see what they would look like. Right. So then it was just, let's just you know, plug in some sine wave, cos wave, whatever, and see what it looks like. So when I was playing, you know, when I was playing around, the math came first. When it comes to the Mandelbrot set, the math comes first, right? When it comes to fractals, right? But
Yeah,
so
I think your fractal model, you need to we need to talk about that in a separate day.
we really should do a fractal session. Yeah,
Sure.
definitely. I mean, the only reason I did this because, well, I actually wanted to start introducing my Aether model to my audience. I've sort of been dancing around it a little bit. But since you brought it up in the last time, I thought, well, this might be a good chance to, you know, just get started on that. And, you know,
Yeah,
but really the fractal paradigm is really my big, you know, it's my true love, I guess you could say.
yeah, your name is Fractal Woman, so I can
exactly.
understand
So
that
obviously, you know, yeah, so that's, you know, and the beauty about the magnet that we talked about last time is, you know, you break a magnet in half, you get two magnets. You put them back together, you get one magnet. So that's the fractal paradigm. And, you know, if the black hole can be a magnet and a magnet's a magnet and the atom is a magnet, then I've got all the scales covered.
Exactly.
And the ether is a magnet. Right? The little electron positron pairs, those are magnets. So then if everything is a magnet, for all intents and purposes, like, you know, then I got it covered.
I think in upcoming session, definitely I would like to talk with you, number one, with fractal concept, and another one concept I think very similar, and people talk about it, I don't know particularly well, is hologram technique. That means self-similarity. People say in the hologram, individual pixel contains the information of the whole. So how actually that works, and how the fractal theory of yours that you're proposing works, I think we can talk about those in upcoming.
Okay, that's a good idea. Yeah, fractals and holograms are definitely related.
Okay,
definitely related.
I think today let's conclude. And do you have any comments or any suggestions?
No, I think we covered a lot of ground, and yeah, I think we can leave it for now. And next time we'll talk about fractals and holograms.
Yeah, thank you for coming, and it was a wonderful session. Thank you. See you next time.
It was. Thanks. Appreciate it. Yeah.
Bye-bye.
Bye.